Sketch the graph of f of x equals the quantity x plus 1 squared over 1 plus x squared by following the guidelines for curve sketching. First, we find the domain of this function. This is a rational function, so we would need to pay attention to the denominator to see where the denominator is 0. This function is not defined when the denominator is 0, but in this case, the denominator 1 plus x squared is at least 1, so it will never be 0. What this means is that the domain of the function f is a set of all real number, negative infinity to infinity. We move on to find any intercept. First, we find the y-intercept by simply evaluate f of 0. This is 0 plus 1, the quantity square in the numerator, and 1 plus 0 square in the denominator. And so this is 1 squared in the numerator over 1, which is 1. The y-intercept is x equals 0, y equals 1. We then find the x-intercept by setting the entire function equals to 0 and solve for x. But since this is a rational function, it is 0 when the numerator is 0, or x plus 1 equals 0, and so x equals negative 1. The x-intercept is only when x equals negative 1, y equals 0. Next, we move on and see if there is any symmetry. To find any symmetry, we simply evaluate f of negative x. We simply replace x with negative x. Everywhere we see an x, we replace it with a negative x. The numerator is 1 minus x, the quantity squared. The denominator is still 1 plus x squared. So this is not the given function. We conclude that the function f is not even. Also, we cannot factor out the negative to make it equal to the negative of the given function. So this is not odd. So the function is neither odd or even. That will not help us with any symmetry. We then find any asymptotes. For rational function, for horizontal asymptote, we simply look at the leading term in the numerator and the leading term in the denominator. The leading term in the numerator is x squared if we were to distribute the second power, and the leading term in the denominator is x squares. So at x go to infinity, the function go to 1. We obtain a horizontal asymptote with an equation y equals 1. The horizontal asymptote is not simply 1, but the equation y equals 1. For a vertical asymptote for a rational function, if any hope of finding the vertical asymptote, we would need to have the denominator equal to 0. But in this case, the denominator is not 0, so we do not have any vertical asymptote. We only found one horizontal asymptote. And then we find where the function is increasing or decreasing by finding the derivative of the function, because the information about increasing and decreasing, or local max and local min, come from the first derivative. To find f prime of x, we use the quotient rule. We square the denominator, 1 plus x squared, and in the numerator, it is u prime, which is 2 times x plus 1 to the power 1 times the derivative of the inside function 1 times v. v is the denominator, 1 plus x squared, minus u x plus 1 squared times v prime, which is the derivative of the denominator, which is 2x. The derivative of 1 plus x squared is 2x. We simplify the numerator by factoring out 1 plus x and a factor of 2 as well. What we end up in the first term in the numerator is 1 plus x squared minus the second term. We factor out 2 already, so there's still 1x and x plus 1. the denominator is still 1 plus x squared squared. This is 2 times 1 plus x times 1 plus x squared minus x squared minus x over the denominator 1 plus x squared squared. Simplifying this, we have 2 times 1 plus x. X squared minus x squared is gone. We end up with 1 minus x over 1 plus x squared squared. We then set this equal to 0 and find the critical numbers to be negative 1 and 1 only. X equals negative 1 and x equals 1. We then construct the sign chart for f prime with these critical points or numbers at cut points. If we plug in any number between negative infinity to negative 1 into the numerator, the denominator is always positive, so we do not need to check the denominator. If we plug in x equals negative 2 from the first interval, we will see that 2 times 1 plus negative 2 is negative 1 negative, and 1 minus negative 2 is positive, so 2 times a negative times a positive is a negative number. If we plug in any number between negative 1 and 1, 0 for example, 1 plus 0 is positive and 1 minus 0 is positive, so f prime is positive from negative 1 to 1. And if we plug in 2, a number in the last interval, we will see that 1 plus 2 is positive and 1 minus 2 is negative, so f prime is negative in the last interval. The function is decreasing and then increasing and then decreasing. We also see that the function f has a local minimum at x equals negative 1 and the local maximum at x equals 1. All these from the first derivative. To determine the interval where the function is concave up and concave down, we would need to have the second derivative. To evaluate the second derivative, we first simplified the first derivative f prime of x, which is 2 times 1 plus x times 1 negative x, which is 1 minus x squared over 1 plus x squared squared. Using the quotient rule, we squared the denominator 1 plus x squared squared, which is 1 plus x squared to the 4th power. Then we differentiate the numerator, which is now 2 minus 2x squared. The derivative of 2 minus 2x squared is negative 4x. We multiply the denominator 1 plus x squared squared minus 2 minus 2x squared times the derivative of the denominator, which is 2 times 1 plus x squared to the 1 power times 2x. This is simplified further. We can factor out 4x or negative 4x. We can factor out 1 plus x squared as well. What we have left from the first term is 1 plus x squared. We factor out 2 times 2x already and the negative sign as well, and 1 plus x squared. What we have left is plus 2 minus 2x squared over the denominator. The denominator is always positive, so f double prime is 0 only when the numerator is 0. Or simplifying this further, the numerator only is negative 4x times 1 plus x squared times 1 plus 2 is 3, and x squared minus 2x squared is minus x squared. This is 0 when x equals 0, or when negative 4x equals 0, the first factor, and so x equals 0. The second factor can never be 0. the last factor, 3 minus x squared, is 0 when x squared is positive 3 or x equals plus or minus the square root of 3. So the three cut points, these are not critical points, but cut points for the second derivatives are 0, negative root 3, and positive root 3. We then construct the sign chart using these three cut points from the second derivative. The cut points are 0 and positive root 3, negative root 3. If we plugged a number between negative infinity to negative root 3, negative 100 for example, into the second derivative, we will see that negative 4 times negative 100 times 1 plus 100 squared times 3 minus 100 squared. This is positive. This is always positive, but this is negative. And so the positive times negative is negative. And so in the interval from negative infinity to negative root 3, f double prime is negative. The sign of f double prime is negative. We then plug in a number from negative root 3 to 0 such that negative 1. We see that negative 4 times negative 1 times a positive number times 3 minus negative 1 squared is minus 1. This is positive times positive. So f double prime is positive from negative root 3 to 0. If we plugged in 1, which is a number from 0 to root 3, into the second derivative, we will see that this is a negative times a positive. So f double prime is negative from 0 to root 3. And similarly, if we plug in any number between root 3 to infinity, 100, into the second derivative, we will see that this is negative 4x, which is negative 4 times 100, which is negative, times a negative number, so it is positive. From the sign charts f prime and f double prime, we combine all of these cut points to determine the shape of the graph. From negative infinity to negative root 3, we see that the graph of the function f is decreasing and concave down. From negative root 3 to negative 1, it is decreasing but concave up. From negative 1 to 0, it is increasing and concave up. And from 0 to 1, it is increasing and concave down. And from 1 to root 3, it is decreasing and concave down. And from root 3 to infinity, it is decreasing and concave up. We then put everything together to sketch the graph of f. Using these cut points as reference, negative 1, 1, root 3, and negative root 3. Keep in mind that we also have a horizontal asymptote that we found earlier at y equals 1. Y equals 1 is the horizontal asymptote. We also found that when x equals 0, y equals 1. So the graph has to go through the point x equals 0 and y equals 1. We also found earlier the x-intercept, and it was negative 1, 0. This x-intercept is also the local minimum because f prime changes its sign from negative to positive. The function f has a local maximum at x equals 1 because f prime changes its sign from positive to negative. And if we were to evaluate f of 1, we will get y equals 2. Similarly, we should evaluate f of negative root 3 and f of root 3 because these are the inflection points where f double prime changes the signs. If we plug in negative root 3 into the function f, we will get roughly 0.13. And if we plugged in root 3 into the function, we will get roughly 1.86. These points should be plotted so that we know that the graph have to go through them. From negative infinity to negative root 3, the function is decreasing and concave down, and since there is a horizontal asymptote on the left hand side, we should stay close to the horizontal asymptote, decreasing and concave down. From negative root 3 to the x-intercept at negative 1, 0, the function is decreasing, but it is concave up, and it has to go through the x-intercept. We might want to be clear about the shape of the graph, so in actuality, it might not be this obvious, but when we sketch the graph, we want to have no ambiguity. From negative 1 to 0, the function is increasing and concave up, and it reaches the y-intercept 0, 1. From 0 to 1, the function is increasing and concave down. From 1 to root 3, the function is decreasing and concave down. From root 3 to infinity, the function is decreasing and concave up, and it should stay close to the horizontal asymptote. From looking at the graph, it should be clear whether the function is increasing or decreasing. So on the left hand side, we might want to fix this so that it doesn't look like it is increasing. It should be decreasing and concave down. The same as the right hand side, it should be decreasing and concave up. Note that it is concave up, but it cannot go up. It stays close to the horizontal asymptote.